Okay, so we're on this slide. I have good news and I have bad news. Which do you want first? The bad news is the test is still on Friday, as scheduled. No. Now the final exam is at 7 o'clock on Friday the 15th, as printed in the syllabus, as announced yesterday. I'm giving you the data that Mr. Asman asked me to give you. The final exam is on Friday the 15th at 7 a.m. in this room. No. Nobody asked what the good news was, so okay, fine. Somebody did? Oh, the good news? The good news is I think I'm going to finish all the topics today, and I'm going to dive in for the test on Friday. I think that's good news, but maybe you don't care. All right, so the last place we were looking at was at this set of gauges for a Pratt & Whitney PT6. We already looked at the torque. Whoops, wrong one. We already looked at the torque. Let's use red. And we discussed the fact that it was interesting that there was two red lines on the torque. Maybe one is a takeoff power setting and another is a maximum continuous, but I personally don't know. The propeller RPM, so this is RPM times 100, so this needle right here is pointing at about 1,550 RPM. On this aircraft, correction, on this engine, that's also the power turbine RPM. Now, granted, the power turbine RPM is probably 10 or 15 times greater than that, but the propeller is bolted right into that extra set of free turbines on that PT6. I'm having strange looks at it that come at me. So on a PT6, it's got compressor. I think it's got a radial inflow. The air goes around, and then there's a turbine or two that drive the compressor, and then there's another turbine or two out here that goes into a gearbox, and that spins the propeller. So there's these free turbines are extracting power, and then we have a reduction gearbox. And then, of course, we have the propeller. So if you went out and spun the propeller on a PT6, you would also be spinning the reduction gearbox, and you would also be spinning these free turbines. And they're free because there's no mechanical connection between the gas producer. So this part here of the engine, this is the gas producer. There's no mechanical connection between the engine that's generating all this power and the turbines that are just extracting it to drive the propeller. That's the definition of a free turbine. You all heard of that stuff, right? Okay, all right. So when I look at this RPM gauge here, which it's really hard to see, this is NG RPM. That's the gas producer. So it's telling me the RPM of the gas producer. So if I've got a free turbine engine, you could argue that one is N1 and one is N2, but that's not the way they're labeling it in this aircraft. They're labeling it propeller RPM, which is the propeller and the reduction gearbox and the power turbines, and then they're labeling the rest of the engine that produces the gases NG. And this is pretty common on turboshaft and turboprop engines like helicopters have turbochaft engines. It's all on helicopters. You're never going to see a helicopter that isn't a free turbine. I'll get to that here before today is over, why that's true. In any case, so you're probably going to see one propeller, one RPM in a helicopter that tells you the RPM of the output shaft, or something that's bolted to the output shaft. And then you're going to see another RPM that has the NG, your gas producer. So you notice there's a red line on the NG, there's a red line on the propeller. We already talked about the fact that this exhaust gas temperature has two red lines. I'll bet you $10 this one with this big flag is the EGT for start. and this other EGT is for all other operations. And you'll notice this says ITT. So there's really at least 3 different ways I can think of off the top of my head to talk about exhaust gas temperature. Exhaust gas temperature, and in this case it's ITT. We've already talked about EGT. That's intermediate turbine temp. And likely on this installation right here, it probably means they're sticking the probe in the middle between some turbines. It's not after the last turbine blade. They're sticking, and it's not in front of the first turbine blade. They're probably stuffing the EGT probe, or this thermocouple rather, somewhere in the middle. As far as we're concerned, I mean, we want to know where the probes are in case we have to do something with it. But still, whether it's an ITT red line for start or an EGT red line for start, we still need to know what that red line is, and we need to know not to go past it. There could also be turbine inlet temperature, TIT. This turbine inlet temperature. And that would be where you would put the EGT probe right smack in front of the first turbine section, the first turbine. So there might be a gauge that instead of saying EGT, it might say EGT, it might say ITT, it might be TIT. And there's 1 or 2 more relatively obscure ones, but those are the most popular 3-digit abbreviations that are talking about how hot is it getting inside of the engine. It's measuring the temperature of gases. Did I lose anybody there? That'd be a great set of test questions, wouldn't it? I think EGT was on the last test, I think. So TOT or ITT would be good questions as to what do these stand for. And you could also say, well, what's the difference between EGT and ITT? ITT probe is intermediate temperature, intermediate turbine temperature, and the thermocouple is stuffed in the middle of the turbine section between turbines. And the TOTIT, turbine inlet temperature, is a thermocouple that's put in front of the first turbine section. I could do that. Yeah, I could say ITT is an abbreviation for what 3 words? And then I could say, where do you find an ITT probe? And don't say on a jet engine. That would not get you any credit. You would need to say it's in the middle of the turbine section. There's at least 1 turbine set of turbines in front of it and at least 1 set of turbines behind it. So let's see, here's oil in PSI. You'll notice there's a red line and there's a green arc and then a yellow arc. And then here's degrees Celsius for the oil. There's a nice green arc here. There's an upper red line and a lower red line. That's actually minus 40. And then fuel flow. You notice it says pounds per hour times 100. So this is reading a little over 200 pounds per hour. In fact, let's see, 2, 3, 4, 5. Yeah, so that's 2.2 times 100. That means it's burning 220 pounds per hour at the moment this picture was taken. At least that's what the gauge said. So the good news is when you operate jet engines, you get gauges. So here is, I didn't catch which one this was. I can't recall. I think this is off of Airbus. It's quite like Boeing. But this is off of a twin-engine transport category jet, an airliner. And it's saying total air temperature. That's for pilots to worry about. It says we're looking at engine 1 and engine number 2. I'll bet you $10 this is only a 2-engine airplane. This fuel in pounds, they're center 1 and 2, so that makes me think that these are the fuel tanks in the wings, or maybe this one in the center is inside the fuselage. But what we're more interested in right now is the main engine gauges. So you notice this is N1. So you think if this is a modern, big ol' honkin' airliner, is it a turbojet or a turbofan? It's a turbofan. So what's another way we could describe N1? They could have labeled it what? What? Fan. Yeah, they could have labeled it fan. Because if it's a turbofan, the fan's the first thing the air hits. So N1 is everything, is what the air first hits, and then everything that's bolted onto it. So the fan's always going to be N1. And you'll notice there's a nice red line, probably at 100. You'll notice it's telling you right now that the engine RPM is 95.4. It doesn't say it, but we know that's percent because we're awesome aircraft mechanics. And it's saying the EGT, $10 that this is degrees Celsius. And you notice here's a red line and then a yellow arc. So if I was going to ask you on the test, what does a yellow arc mean on an aircraft turbine engine gauge? Because on condition has a certain meaning. On condition on an aircraft part means I never have to replace it or overhaul it. If it's working and it looks good, I got to keep letting it run. Under certain conditions, yeah. You don't have to use the word under certain or conditions, but that would work pretty well. There's only a certain time or place or circumstance that you can operate the engine in that RPM. Exhaust gas temperature. So, Jason, you screwed up and raised your hand. So, what do you think is the condition under which you can operate in that yellow arc on the EGT gauge? What's your guess? It's a precaution, that's true. But when is it okay for the in that yellow arc? When is it okay? Hang on. Give me a second. Yeah, I know you're guessing. So you're saying that you can operate in the yellow during start? Okay, that's an interesting thought. But does that, so... When you say in the bad zone, that means I'm going to go to purgatory? Bad? Not allowed. Well, yellow arcs are generally allowed, but only if only under certain set of circumstances. So let me ask you this question then: Is high EGT good during start? In general, is a really high EGT good? Yes, no, maybe. Okay, no. What we prefer is what kind of an EGT during start? If we could have our choice, we'd have what kind of an EGT during start? High, low, medium, or beats the snot out of me. Those are 4 choices. Okay, all right, I'll accept medium. I would have said low. The lower the better, right? Because what's the number one thing that you do under normal circumstances, Jason? I'm harassing you here because it's fun. Thank you. What's under normal circumstances, what's the worst thing that we normally do as aircraft mechanics, or pilots for that matter, do we do to jet engines? But it's normal for us to do it. But it's the worst thing we can do to a jet engine. You're close. What happens if the EGT gets... Oh, it's okay. But is that really good for the engine? No, it's not. Okay. So, when is the EGT get the hottest of all the times we operate engines? And it's normal. So, what's this thing we do to jet engines all the time that is normal, but it's the worst thing we could do to it? Okay, I'll back up one more time. What's worse? How long do you have? How long before you go past the red line does it take before you call it a hot start? How many seconds? A hot start. You're thinking of some other thing. Let me ask you this question. Okay, yeah, or less. Or less. If it goes above the red line, you got to ride it up, and now you got to look at the maintenance manual and figure out, do I have to take this thing apart? So how fast can you fry a turbine engine during start by having a hot start? How fast can you do that? 5 seconds or less. Okay, so how long can you run the engine without an oil pressure needle starting to move?
5 seconds or less.
The oil pressure. Just like a reset, just like your car. It's all the same. Every engine I ever saw in my whole life, If the needle doesn't start moving within a certain number of seconds, you have to shut the engine down and figure out what's wrong. No, how many seconds? You said 30 seconds. But what can you do? What can be happening for up to 30 seconds? But at 30 seconds, you got to shut the engine off. It's not EGT. The oil pressure, the oil pressure. Which can ruin the engine faster? A high EGT or no oil pressure? High EGT. All right. So now, time is now a thing, right? How long? Now, what if we see this needle going up and it goes up into the yellow arc? Is that good? I'm not going to belabor the point. Is that yellow arc? The yellow arc is going to be different. When is it okay to be in this yellow arc on that gauge on that engine is going to be different than when it's going to be okay to be in the yellow arc on a different engine. So we got EGTs. Let's see what else we got. Look, here's N2 for engine number 1 and engine number 2. So this is a 2-spool engine, a dual spool engine. We got fuel flow. It's interesting that all these numbers are identical. In real life, the engines wouldn't be identical. So that makes me think somebody put this all together. Really? The GT is to the nearest decimal? Probably not. We got oil pressure, we got oil temperature, and then it's the Beach Boys song. What? Good Vibrations, yeah. Is anybody familiar with that 1963 hit by the Beach Boys? Good Vibrations. Do anybody want me to sing it? Remain seated. Okay, I'll sing it. I'm just kidding. I'm not going to sing. So I don't know what it is for this, but I'll bet you $10. This is a computer. I bet you if this number gets too high, it probably turns color, and you probably get some message up here that says bad vibrations, dude. I mean, did they have dude in the 60s when the Beach Boys? Did they have dude then? They had dude in the 60s? How old was the Big Lebowski in the 1960s? Question, Chan?
Yeah. A couple days ago, we took notes that the starter motor is hooked to the N1 to the inner engine.
Well, that may be what's written in your notes. The starter motor is always hooked up to and if I said that in class, my apologies, but the starter motor is always hooked up to the highest N number there is. Whatever's deepest inside the engine, that's what the starter motor spins. So on this engine, the starter motor would be spinning N2. Now, as N2 starts spinning, even before you turn on the fuel, it's blowing air through the engine. So N1 might just barely start to be rotating. Even though the starter isn't directly bolted to it, we're blowing air across the turbines. Did you have a question in there? Keep going. Okay. All right. So just to be really clear, N1 is the first thing the air hits and everything is bolted to it. So N2 would be the second thing that the air hits and everything bolted to it, including the turbines. And if you have an engine with 2 spools, an N1 and an N2, the starter's always going to be connected to and spinning the N2, whatever's deepest inside the engine. Whatever's think about it like this. Whatever's closest to the combustion chamber. And in an engine with N1 and N2 is going to be closer. Rolls-Royce likes to do N1, N2, and N3. They got several big, giant turbo fan engines, and they got an N1, N2, and an N3. And guess what? The starter spins N3. That answer your question, Chan? Yeah. Okay, so I found this, and I wanted to have an example of a gauge that would tell you vibration. So I'm very happy I found that gauge. Yes. What is it measured in? Oh, gosh. Well, at 2.2 hertz, that's 2.2 vibrations per second. I think that RPM is in that's questions. Yeah. If it vibrates at a certain frequency, could I play a note at that frequency? I don't think I could sing 2.2 hertz. And it probably isn't 2.2 hertz, because nothing's spinning that slowly in a turbine engine, even at idle. Even the propeller on a turboprop at idle is spinning more than 2.2 times rotations per second. So I believe this is not a measurement of the frequency, but a measurement of how strong, how hard it's vibrating. Just per second. It's probably related to a certain amount of force. But I mean, ask me about what state of Jalisco, what state in Mexico you can make tequila, and by Mexican law you can actually call it tequila, and I have a lot of knowledge, but at the moment I can't tell you what that 2.2, what the units are. Another question, Ashton? If a blade came off, this would go ridiculously high. Yes, that's correct. Yeah, you might say more than just oh crap. So here is an instrument panel. I know it's a drawing, but this is out of a Bell 206 with a C250 turboshaft engine in it. How many rotating components are inside of the main engine of a C250? Is it all one shaft and everything's bolted to it? Or is there more than one shaft inside? I'm not talking about the gearbox. One person says one shaft. How many people agree with that one person? The Rolls-Royce C250, you know, the ones that you all have worked on many times? Everybody keeps saying one. You're all wrong. No, not the gearbox. Inside the engine, there's turbines that drive the compressor, and then there's a separate shaft that drives the gearbox. Silly students. Literally, well, I'm gonna show you. I got to show you a picture. So that's the only way I can do it. So here's the gearbox on a C250. And there's a shaft in here, and there's a turbine on it. And then there's another turbine or two, and that is driven by the compressor. So this right here, that's the gas producer. You could also argue we could call that N1, and then here you could call that N2, and sometimes that's called the power turbine. The trick is that you've got to somehow get the starter motor to spin that shaft, because you got to get the starter motor to spin at least a compressor somewhere. So this is not how it looks on the inside. On the inside, it's really, I've got this turbine right here. Whoops. I've got a turbine right here, and then I have this shaft, and now I have the turbines and the compressor. So remember, this is effectively like a cardboard tube, except it's made out of metal. And here's the gearbox. Both of these shafts go into the gearbox. So I can have a starter motor on here, starter generator, and that power, whoops, I don't want it to go to that one. The starter, the power can go to the shaft and spins the gas producer and spins NG. So this part here is NG, it's lowercase g. But this power turbine, that's what we want to leave the engine, so you can put a gear tooth around it and other gear teeth, and it leaves the gearbox. So I'm guessing you didn't take the engine down far enough to get to the fact that there's a second. When I say shaft, it's actually a tube. This part here is actually a tube, but we call it a spool or we call it a shaft. It's a free turbine. That is, this turbine is free to spin. It is not mechanically connected to the power, the gas generator. And while I'm at it, every single helicopter engine out there is a free turbine. How many helicopter pilots are out there? How many helicopter mechanics are out there? I'm the only one of each? Okay, all right. Well, then I'll tell you the answer. It's because you only want the starter motor, you want the starter motor to be small, and so you only want the starter motor to spin the gas producer. If the starter motor, if this was a fixed shaft engine and this was bolted together, the starter wouldn't just have to spin the gas producer, it would have to spin this turbine, and this turbine spins gears, and it leaves the gearbox of the engine, and then it would also have to spin the gearbox of the helicopter and spin all the rotor blades. How big of a starter motor are we going to have then? Massive. I like that, massive. Because it would have a lot of mass and a lot of weight, and then that's a whole extra passenger we couldn't put on our helicopter. So you're never going to see a fixed shaft turbine engine on a helicopter. Because the nice thing is, effectively, that means there's a clutch, but it's built into the engine and it doesn't have any weight. You can actually take on that gearbox that goes up to the main rotor blades, you can actually put a disc brake assembly on it and hold that disc brake, and you can actually hold the rotors and then start the engine up and spin in the gas producer. And that way the rotor blades don't spin around and chop people's heads off. When was the first Dawn of the Dead movie came out? Was it like in the late 70s? Is anybody a slasher zombie fan? That's the one where Bell 206 main rotor blade chops somebody's head off and makes him look like Frankenstein. In reality, somebody's skull wouldn't chop off that easily and be jagged and stuff. But if you want to know about body destruction when it hits aircraft parts that are rotating fast, see me after class. So we're back to our Bell 206. And so now we know that we have a free power turbine in addition to the gas producer. So just for fun, I'm going to go straight to the gas producer. It's hard to see those letters right there, but this is NG RPM. So as aircraft mechanics, this is going to be one of these RPMs that we're going to look at. And if that's what the starter is spinning during start, this is the main RPM gauge you're going to be looking at during start. Same thing on a PT6. When you're starting a PT6 that has a free turbine, you're not looking at the propeller RPM, you're looking at the NG. And just like in that PT6, that power turbine, the free power turbine is hooked up to the propeller. They call it propeller RPM. And a helicopter, they got a T on here. And T is for turbine. But that's really the power turbine, the free turbine. And that's the one the pilots look at a lot, because that's what's driving the rotor blades. And if you fly helicopters, when the rotor blades don't spin fast enough, you die. So helicopter pilots are really... What's the G? The G stands for gas producer. That's the part of the engine that has the compressor and the combustion chamber, and it has the turbines that drive the compressor. If you took the power turbine out, it'd still be a jet engine and it would still run. But we need to extract energy in this case, to drive the rotors, the transmission and the rotors. So we put that extra turbine in there, and that extra turbine drives the transmission, drives the main rotors. Question, Jacob? What's this little blue line on? You're looking at that blue line on the airspeed. Well, if it was a multi-engine airplane, it'd be velocity of minimum control if the critical engine went out. And at the moment, I'm thinking about helicopters and a blue line on the airspeed indicator on a helicopter. And at the moment, I don't know. All right, so we're going to use the NG gauge, and of course, this one has a turbine outlet temperature. Look, here's a red line, and look, it's got a dot. So can anybody tell me if I showed you this picture on the test and I said, what's the dot? Probably. It's probably the starting on the smaller engines, the starting EGT is usually higher than the main EGT. On bigger engines, it's usually reversed, but I'm not going to ask you that on the test. Yeah, if you said one of them is a red line for start and one is a red line for all the other operations, then you'd get full credit. So that's great. I like the fact that this gauge has both of the red lines on there. But one of them you're only going to look at during start. And of course, there's a yellow arc. This is a helicopter, so I would bet money that the condition for this yellow arc in here is 30 minutes. So if you're in a hover over a building with a big air conditioner, you're not at takeoff power if you're at a really high power setting, but if you run the engine more than 30 minutes at this high of an EGT, then you're going to start damaging the engine. So let's see, here's what I find interesting, is this has two needles. The R is for the main rotor. We're not worried about that, but you'll notice this is the turbine needle, and these two red lines right here, that's the normal operating range. Look how small that green arc is. I'm not going to get into the aerodynamics of helicopters, but helicopter rotor blades need to operate at a very small range of RPM. And interestingly enough, helicopter engines, you run them up to full 100 RPM, and then for the entire rest of the flight, they stay at 100. In fact, you don't have to write this down, but all helicopter engines have a governor. So when you start that engine up and you roll the throttle on and go past idle, it'll go up to about 100%, and then and the pilots, when they don't change the RPM. In a helicopter, when you move collective and you lift up and the rotors go to a high pitch and the engine starts slowing down because the rotors are asking for more power, the governor inside of fuel control will squirt more fuel in. When you ask for more power, this RPM will stay right smack where it was, hopefully right here in the middle of the green arc. And all you're going to notice is that your EGT, your turbine outlet temperature, is going to go up, and you're going to see your torque go up. And you're probably, where's the fuel flow? No, fuel flow, I feel bad. I'm not seeing fuel flow. I'll be dogged. No fuel flow. Okay. So I just wanted to show you a different set of gauges that are still telling us very, very similar things. So here's another set of gauges. This is a two-engine job. I personally don't like the way they put it. Here's fan left, and here's fan right. And why they said, and look, here's engine left for temperature, so this is EGT. And here's engine right for EGT. So I like them running up and down. That's the way they usually do it. So here's a fan, based on what this indication says, it's doing 75, 76, 77, 78. So there's 78, and this says percent RPM. And can you use the fan RPM to set engine power? Yeah, you're all going to get this wrong on the test. What are the three typical gauges you use on turbine engines to know how much power the engine is producing? EPR is one. And, go ahead. N1 is the same as the fan. And then torque. If you're using a turbo shaft or a turbo prop, it's going to be torque. So this is also the same as N1. So here's a red line EGT, a red line EGT. Look, we've got fuel. Go ahead. Yeah, we covered it yesterday or the day before. It's on a slide in black ink on the screen. Well, not black ink. Whatever photons were coming out of the screen. Yes, you need to know on the test that fans are always N1. So here's fuel flow, pounds per hour times 10. So right now it says there's 25, there's 30. That looks like about 29. So 29 times 10, we add one more zero. Pounds per hour. So this is going to be a smaller turbine engine. And look, here's a percent RPM. Well, here we got fan. What's this percent RPM? It's not labeled very well. What would we call it, because we're so knowledgeable? If there's 2 RPM gauges on an engine, that means what? It means there's at least one other shaft inside the engine spinning around. Now, if it's a turboprop or a turbo shaft, it's almost always going to be NG. But if this says fan, that tells me it's a turbo fan. They usually don't label these things NG because they don't have an NG, because they don't have a free turbine. But if the fan is N1, then this gauge is probably almost for sure Ashton. No, NG is almost always on turboprop and turbo shaft engines. If this has a fan, that means it's a turbo fan. There is no gas producer because it has N2 or N3, yeah. So, interesting test question. Of all these gauges, which one is the starter motor hooked up to? N2. The smallest, most deepest N number that's down inside the engine. So there's another good question. If you are, did I delete it? Oh darn, I deleted it. If you're starting up a turboprop or a turbo shaft, what's the starter motor hooked up to? The gas producer or the power turbine? Let's say you got a PT6. I think I got PT6. You got a power turbine and it drives a gearbox and it drives a propeller, and then you got a couple of turbines and that drives the compressor. Which of these is the free power turbine, the one on the right or the one on the left? This is a propeller right here. Okay. So this is the power turbine. It's also called what kind of a turbine could you call it? In this case, it's a free turbine because there's nothing mechanically connecting this shaft to that shaft. So, where's the compressor on this engine? It's on the gas producer. So this is going to be NG. G is for gas producer. And here's the compressor. So during start, do we need some outside air to blow through the engine? During start? Do we need a lot of outside air to blow through the engine? So which one of these two shafts do we want the starter motor to spin? NG, which is also known as the gas producer. That's where this G came from. Because really all this engine in here is doing is making gas that will blow through the power turbine. That's all this part does. It's just there to generate high velocity, high volume gas. It just happens to be hot, but that's the only way we know how to do it. So there, this is my second to the last picture I had of engine gauges. Name that airplane. Spruce Goose. Now it's hard to read back there, I know. So the top gauge says pressure ratio. I think it's talking about EPR, engine pressure ratio. And this one right here, this is RPM in percent, and this is EGT. And this is fuel flow in pounds per hour times 1,000. So that's reading just under 6,000 pounds per hour. Well, I think that this aircraft has the power system turned off, so the gauges aren't working correctly. How many engines are on this aircraft? Name an aircraft with 8 turbine engines. Yeah, I can't think of another one that has 8 turbine engines. Spruce Goose had 8 Our 4360s, 4,360 cubic inches, approximately 3,500 horsepower each on takeoff. They weighed around 3,500 pounds each. They were very large radial engines, which when you look at the airplane, they look kind of small. So just for fun, I put this picture in here. Now you can see those, this is in color, but now you can see those 10 sets of main engine gauges and the throttle quadrant. Somebody's got on a Nomec flight glove. And then there's some interesting TV sets out there. I'm sorry? What's the question? So that's what it looks like. That's the engine gauges on a B-52. This stuff down here, the co-pilot's really a flight engineer. This is the fuel system and the pressurization and the electrical system and the hydraulics. This instrument panel goes from down here all the way over. Even there's more stuff over here. So there's no flight engineer on this airplane, but so the co-pilot plays flight engineer. Maybe we didn't get to this slide. Didn't we talk about N1 versus fan before? Oh, all right. So we've looked at EPR. Talked about takeoff power is typically limited to, maybe I just accidentally stuck this in there. Takeoff power is typically limited to how many seconds? No, I'm just kidding. Okay, how many minutes? 5, okay. Okay, I'll try to remember that. So here's a page. I know it's really hard in the back to read the numbers there. But what I want you to get off of this chart, this is a Boeing chart, and this is what a mechanic would use out of a maintenance manual if they were going to do an engine run. And so ambient temperature, this is really OAT, so I'm going to make it really big. OAT, outside air temperature. In this case, it's degrees Fahrenheit. So that's 12 degrees Fahrenheit. Here's 16 degrees Fahrenheit. Here's 20 degrees Fahrenheit. And then these columns right here are barometric pressure. And you may not have recalled on earlier days this week that when you go out and run an engine, it might run a little bit differently if the temperature is different and if the air pressure is different. So in order for you to know what fan speed so it's got to be for that particular engine and airframe. So I'm not going to go into this too much, but essentially it's talking about an idle RPM. So look at this. That says 63.5, and here it's talking about an EPR of 1.50. And it's hard to see it up here, but it says where did it say? Plus or minus 0.05. So that's not a very big change, and that's not very much RPM difference, is it? Here, let's look at this one. I don't like that one. Regular minimum idle N2 is 57.7, and it's hard to see that back there, but it says minus 1.5 to minus point. Maybe I just crossed it out. It ought to be plus to minus. There it is. Okay. I just can't see, and you can see even less back there. So it says 57.7 plus 1.5 minus 0.5. So what that is essentially saying is idle ought to be 57.7, but it can be 1.5 RPMs higher. It can be a half of an RPM lower. And if it's 29 inches of barometric pressure and it's 12 degrees Fahrenheit, then that's the normal idle, 57.7. It can be 1.5 higher. It can be 0.5 RPMs lower. And it's the same for the EPR. Let's see, takeoff EPR, it says so right here. It's hard to read it out there. It says takeoff EPR is this number here, 150. 150 plus 0.01, that's not much, minus 0.0. So the EPR, it can be a hair too high, but it can't be any low at all. Now, I'll bet you $100 this is on a computer-controlled engine. This has a full authority digital electronic control. You could say it's an listening at the outside barometric air pressure and the current air temperature. But what if your airplane engine is on the ramp? It only has to be plus or minus 2. Here's our plus or minus 4. This is 12 and this is 16. So I'd read the instructions somewhere, which I can't see, but it probably just says pick the closest one. All right, we're getting close. We're going to finish this tomorrow. But it'll probably take us 5 minutes on this slide, and then the rest will be a really, really, really fast review.